Welcome. I think we'll go ahead and get started. So welcome to the I4Energy series. This is a seminar series. My name is Therese Peffer. I'm the Assistant Director of I4Energy. And before I introduce today's speaker, I wanted to make an announcement. Citrus is on Twitter at Citrus News, so you can follow us there. At the end of today's talk, the question and answer session and the our online webcast viewers can ask questions live via Twitter using the hashtag #CitrusI4E. So I'm very happy to introduce today's speaker, Stephen Dawson-Haggerty. Steve is a 6-year PhD student in the Locale group in the Computer Science Department here at UC Berkeley. His current work is on a next-generation architecture for control systems for a future where a time series from transducers is ubiquitous and systems are constructed by federating multiple heterogeneous components. He has a background in embedded sensing and networking, conducting large-scale deployments of wireless sensors in and on forests, volcanoes, and commercial buildings. He is a principal developer of BLIP, the low-power IPv6 networking stack for the TinyOS operating system. And with that, please welcome Stephen Dawson-Haggerty. Thank you.
Thanks, Therese. Thanks everybody for coming. So I'm really happy to be here today to talk a little bit about this project we've been working on for the past couple of years across the street in EECS called sMAP, or the Simple Measurement and Actuation Profile. And in particular today, I'm going to be talking a lot about how this project has been applied to our work in commercial buildings. And so just for the sort of cursory overview for why we're in commercial buildings, the basic answer is energy. They're 39% of primary energy and 73% of electricity consumed in the United States. And they're also a huge ripe target for optimization and novel applications and doing things differently because there's so much energy. And we're not interested in energy just for the sake of energy, but we're also looking at some underlying trends that are driving us to try to change the way we consume energy in addition to just reduce the overall carbon footprint. One is, especially here in California, we have these really aggressive carbon targets like Energy 2050 that's going to reduce carbon to 20% of 1992 levels. That's driving us, and that's led to much more renewable resources on the grid. And the other trend that we see is that the cost of instrumentation has fallen to the point where the instrumentation compared to the installation is almost free. So you can instrument everything, you can measure everything. Actuation is still a little bit hard, but in the future, I think everybody in this room probably believes that instrumentation is not going to be the thing that's holding us up. And there's a really interesting coupling between these goals because you end up bringing these generation resources on the grid that have almost no flexibility about when they generate, which is a total turnaround from the way the grid operates today. And so our research has really been driven by the idea that if we can control when the loads consume the energy, we do a lot of very aggressive demand-side load management, we're going to be able to really enable these carbon goals. And then you look at the energy pie and you see that it's 73% commercial buildings, and that's why we're in commercial buildings. You might think that as computer scientists, we would have been in data centers, and we tried that for a while, but data centers are sort of 1% to 2% of the electricity consumed. And so Amdahl's law tells you that no matter how well you optimize that, it's not going to matter. And so we moved on. So commercial buildings. We're in a commercial building. It's a pretty nice commercial building. They're very complicated environments, as we learned to our surprise, sort of from the get-go. On the outside, they have sort of their physical structure here that's the spatial extent, the orientation, all the things architects want to build. And when we talk to architects, what do they care about in a building? They want it to be pretty. They also want it to be usable. But their overriding concern is that it be beautiful. And I think, especially in this picture, Citrus is a very nice building. But then you get inside, and there are also all these other systems inside of the building that are there in order to manufacture a nice environment for the occupants. And these are things like lighting systems, which have controls. There's occupant activity, which impacts the energy there. There's space conditioning, so HVAC, heating and cooling loads. There's process loads. This building we're in is a little unusual because we happen to have a nanofabrication lab over there that's consuming 700 kilowatts of electricity. So this is run-of-the-mill commercial building, except for that part of it. There's security systems that monitor when people come and go and make sure that there's things, and all sorts of other life safety systems. But the predominant characteristic of all these systems is that they generate a whole bunch of data, but it's all kept within vertical stovepipes. So the security system talks to campus security for your card badge data, but no one else. The networking system is managed by an entirely separate group and talks to no one else. The HVAC is separate from the lighting, although there's a little bit of a, that depends a little bit on the building. And then there's all this occupant data based on class schedules and course schedules and day of the week. And so there's an enormous opportunity for co-optimization of all this stuff. And we haven't even talked about the stuff that's outside of the building yet. So just to give you a brief example of the scale of what we're talking about in this building, which will be sort of a running example, although we have a bunch of other buildings that I'll touch on at various points. Just the sort of process side of this building, the HVAC loads, the lighting loads, have somewhere around 6,000 sense and control points. And this sort of surprised us because, coming from a SensorNet point of view, we thought that we would have to put in all this instrumentation. We'd have to really dive in to create the detailed kind of data, find the detailed kind of data we need in order to connect the building to these loads. But really, the data is already there to a large extent. There's lots of temperature data. There's lots of lighting data. There's lots of energy data, specifically in this building, since it's built as a test bed. And there's also the ability to make changes to the system because the building management system is what runs it. So there are 2,000 control outputs in here that control pump speeds and light points and damper positions and everything. But the thing is that the vertical architecture that I talked about for all these systems applies here too. And so within the building management system, it's really designed for a world where all of the optimization happens between sensors and actuators connected to a panel. So you have a door switch, and when you open the door, it turns on the light. It's really not designed for a world where you might be doing model predictive control and looking at weather forecasts a few days out, or a world where the occupants can hit a button on the web page and change the way their space is conditioned, or a world where you look at the network data coming out of the switch and use that to inform whether or not you think anybody's in the room. And once you do that, it just becomes a huge headache because all these systems, if you just stick to implementing stuff within one of them, it works pretty well. They're legacy in some regards, but they weren't designed completely arbitrarily, and you can do a lot of what you want. And it really starts to break once you start introducing external data to this world, which is, of course, where we're all going, whether it's AutoDR or OpenADR giving us demand response events, or whether we're tracking a price signal from the ISO, whether we're looking at the reservoir levels. We're not really sure what we're going to be doing, but I think we're pretty sure that whatever sorts of new kinds of optimizations we're doing and load following that we're generation following that we're doing are going to require a bunch of analysis and external data. And so at a really high level, the research agenda sort of has proceeded along these three-phase sort of monitor, model, mitigate pipeline, where first you figure out what's happening, then you're going to model the way the system is working, and then you're going to reduce energy consumption. But this sort of has a more sort of active corollary that I think is sometimes useful to talk about. And what are we actually going to do in order to monitor, model, and mitigate? Well, what we're going to do is we're going to collect that data. We're going to put it somewhere. We're going to process it. And then we're going to actuate it. And so any framework or any system that we're going to look at in order to do this really needs to have something that fills all three of these checkboxes. So just as sort of a straw person argument, is this already done? Is this a solved problem? Should we be using some industrial protocol for this? We've gained quite a lot of experience with industrial protocols over the past couple of years trying to just extract the data from a bunch of these systems. And I think it's pretty clear that if you talk about this problem sort of writ large, where you're doing this wide-scale distributed optimization, industrial protocols are just the wrong answer. They're built for a very small closed world assumption where you're in a factory and you're talking between pieces of equipment on the floor, or you're in a building and the damper needs to talk to the thermostat. They're not built for a world where things are going to fail, your data is going to be incomplete, the network is going to be unreliable, and you're going to have lots of other problems. And so, and the other issue that comes up is those stovepipes. So every building is going to have multiple generations of legacy hardware and software in the same building. And you're not going to just throw it out. You could do a green slate design, and you should have the ability to do your perfect building. But the reality is buildings last a long time. You're not going to throw everything out tomorrow, no matter how good your new system is, because it's not going to be good enough. The typical vertical system is very expensive to integrate with, and then even if you did integrate into it, it wouldn't do what you wanted. The data is designed to go in at the bottom, come out the top as a set of sort of canned analyses that they expected you to want to use, in total opposition to sort of the internet school of thought where it's a platform and you can build whatever you need for that particular thing. Also, curiously, there's a number of other problems with scaling up existing systems. There's limited access to real-time data. For instance, in this building, accessing trend logs for today is much harder than accessing trend logs for yesterday. But you're not controlling the building against yesterday. You're controlling it against what it's doing now. There's also no description of the what or the why in the system. So you get a point of data out of the system from a thermostat or something, and maybe it tells you it's in Fahrenheit or Celsius, but it doesn't tell you anything else. It doesn't tell you where it is. It doesn't tell you why they put it there. It doesn't tell you what zone it's in. It doesn't tell you any of this semantic level information that you need as soon as you start to try to build a model of the system. And one of my colleagues sort of compared the state of building programming to programming in assembly language, where you need to know, where you're doing very atomic, low-level operations all the time. And so this is sort of the state of the world and the state of the problem that we faced when we started looking at this problem. And so what we decided to do was to develop something that we would be happy with going forward, but could also look backward and respect sort of the legacy that's there and integrate with the legacy that's there. And so sort of simply just to say what sMAP is, it's sort of two things. One is it's an open representation of physical time series data that's self-describing, that you can attach metadata to so that when you have that thermostat stream, you can know it's a thermostat stream, and maybe you can know where it is, although the details of that, of course, are dependent on how well you can figure that out. And furthermore, it's also a platform for using this physical data, which is something that none of these existing systems really fit the bill for. And what we mean by a platform is it's not the end goal to build this great system that does all of this monitoring, modeling, and mitigation. It's designed to, we do some of that, but it's also to provide building blocks so that when you want to build your application with real-time data, you're not reinventing the real-time data analysis stack or the time series database or any of this other stuff so that you can innovate in just your little part of the puzzle. And so the components of that are the real-time access and archival access, which is really important to integrate since you'll want to run your analysis on archive data and then put it into production on real-time. Drivers for talking to all this legacy stuff. Subscriptions so that I can send my data wherever I want, and sort of basic first step interfaces for query processing, visualization, so that out of the box it does something useful. And that's sort of an important sort of open source software principle, which is the whole problem with platforms is you bring your platform to somebody, let's say you're trying to sell it or something. You bring your platform to them and you say, well, and they say, what does it do? And you say, well, whatever you want. And then they say, well, I have this problem. And they're like, well, you're like, well, it could solve that problem, but it'll take some work. So the important thing in open source is to solve a particular pain point. And then once you get people hooked, then you can show them that it solves a bunch of other problems too. So our design goals were essentially what I just said. We want to integrate the heterogeneous monitoring and actuation. And we've sort of proven this out through a large number of deployments across different communication substrates. What we have done SCADA integrations and Modbus integrations and serial port integrations and all sorts of wacky protocols that are left around. It's also important that it be scalable in a bunch of dimensions. It needs to be scalable to a large sensor density, like in SDH, where we have 6,000 points. But it should also be scalable so that when we start doing these wide-scale optimizations, we don't need a new system just because now we have a campus instead of just one building. And this is one place where we start looking at things like, what does it mean to be robust? And what sort of metadata is going to let us scale up to that? We've got some other things to make it usable. It's got to be fast. It's got to support a representative set of applications efficiently without bending over backwards. And so what we ended up with is a architecture for doing this in which we have a separation of concerns. So sort of at the bottom level is the instrument tier, where we're pulling in time series data from motes, from embedded devices, from SCADA systems, from anything, and adding metadata tags to it wherever we can to describe what it is, and really abstracting the underlying heterogeneity there into a simple interface that anyone can talk to. And this is also responsible for transmitting that, because one element of scalability is, let's say I'm collecting data, not from Citrus, which has an excellent internet connection, but from someone's home, which doesn't have an excellent internet connection. The design point is somewhat different there. So if you don't build reliability in at the instrument layer, you're going to end up with a lot of holes in your data that you didn't need to have. That provides the real-time sort of flood of data from all these front-end devices. But really, most applications aren't that interested in that. The control loop applications are interested in real-time data, right? But most modeling and visualization applications are actually much more interested in the record of readings that we've seen. And so that's sort of the other main part of the architecture, which is the repository, which is sort of like a much better version of a historian, and if you're from the process control world. But really a platform. Instead of being something simply for trending or for viewing time series, it's something which is a platform for other applications which are going to consume that historical data. And that means doing things a little bit differently there. And then, of course, on the left, we have all the cool GUIs and models and stuff that people will build on top of that. And so just to get down a little bit into the nuts and bolts of what we're actually going to do here, the S is for simple. We wanted to make it simple, so that you can implement this efficiently, compactly, and suck up any sort of legacy. One of our original design goals was actually to make this so that you could stick it onto an embedded device that's running 6LoWPAN and have it speak this natively. And so that's our way forward. Our way forward is devices will implement this natively. And so what that means is you can't do too much. What we do is we say that the world is either a time series or a collection of time series. And a time series is just a time-stamped sequence of observations, right? That's the kind of data you always get. One minor distinction there is the semantics of time, of course, are sort of fundamental to time series. And one way people often define them is as having a fixed period. We found that was a really sort of constraining assumption to make. So you would say this sensor samples every 5 minutes, and the readings will happen on 5-minute boundaries. And so it's actually important not to do that, and rather accept the fact that the readings will be jittered, and then fix it later. We stick all these time series into a simple JSON schema, which is this JavaScript object notation that anyone can parse or generate by hand if necessary. And so here we have one time series, which is the sensor 0, channel 0 time series with a timestamp and value. And we've durably identified it with a UUID, which is just sort of a 64-bit number that you can generate uniquely with very high probability. And what this lets us do is it puts all the time series data in the world into a single namespace, and then tag it with key value metadata. So for instance, here we've tagged it with the source name is my example sMAP source. And for the purposes of sort of actually implementing this and sucking up all the data, it's important that you be able to do this very easily. And so within the resource tree that's exported by these JSON servers, the metadata applies hierarchically. So at the root of the sMAP server, you might say that all the data under here is in Corey Hall. But then maybe we'd have a sub-resource called GPE, which is a PowerScout 18, which is a 6-phase electric meter. And maybe we'd say the first phase of that is measuring lighting on floors 0 through 4. And that phase ABC is measuring phase ABC. And finally, we'd get out to the point where we can say that this particular time series is a floating point number in the US West time zone that's measuring kilowatts. And so using this, all the other tags apply to this one, but only the kilowatt tag applies to this particular time series, making it really easy to sort of map your existing time series data into a more organized form of your time series data. And part of the research effort has just been to generate a representative collection of drivers and implementations of this so that it's actually useful. So focusing on how easy is it to integrate your time series data into this framework. If you expect people to do it, it's got to be really easy. Adding some things which aren't there by default. So reliable delivery with local buffering has been a huge sort of sell point for this design, because otherwise everybody ends up implementing this again themselves for that off chance that the internet's down today. You have to be able to add the metadata here so that you can separate the driver logic, which is specific to talking to a particular instrument, so my Dent Industries one, from site-specific configuration, like the fact that I stuck my Dent in Quarry Hall. And building out the driver library tutorials and getting that minimum effort down to add a new source. And we've been really successful within our group and outside of our group, actually, for building up a driver library for talking to lots of obscure industrial protocols and sucking the time series data into this framework. We've done a whole bunch of ISO data. We have thousands of price streams from the web. We've got 6-low-pan meters. We've got Modbus meters, which are these Dents. We've got Cadillac meters. And in fact, Domenico and Scott have been instrumental in installing a lot of these in our buildings, where we pull down data from all the buildings on campus, from the campus obvious portal. And then we've done some more sort of hardcore industrial protocols like OPC, which is OLE for process control. It was considered very good in 1995. And then also sucking up data from a variety of other building management systems. And the nice thing about working in buildings is, like I said, they're also often really pretty. So here are some gratuitous pictures of buildings we have data from. The David Brower Center is running a BACnet stack on Windows. New York Times sort of exports CSV files. We had a giant deployment of 6-low-pan, which is a low-power IPv6 mesh networking standard in Building 90 that's was sucking down a few thousand channels of data from 500 moats, and then a bunch of buildings on campus. So that's sort of the instrument side of sMAP. It's really just the nitty-gritty of figuring out how to talk to all these different control systems, mapping it into a single common plane, and then getting it out there into the world where people can use it. And you might have various concerns about this. In particular, did we encounter any data models in these, or metadata in any of these control protocols that we couldn't represent in sMAP? And the answer really is no. There's so little metadata, and what you have is so valuable that it's all maintained sort of ad hoc in screens and stuff that we're really able to just get it down to tags. So now I'm going to change gears a little bit and, for the second sort of third of the talk about the archiver, which is the software service that provides the real access to the data that most people use. And this is a place where we think that what we're doing is pretty cool. And it sort of focuses in on 3 key challenges you have when you have a large amount of time series data. One is just finding your time series. We have 100,000 time series going into the database. Just finding the 2 you want is a real challenge. It's not a problem that people think about if you're doing all your analysis in MATLAB with really high-value data. But a lot of the data we have is relatively low value. And so it's occasionally useful, but you have to be able, but being able to find it is even more useful. And so so the location and the querying are sort of how you label and tag and pull your data out. And then the final part is, in order to make it useful, you also generally need to do some sort of data cleaning. And this is something that's not done in traditional process control historians. And what we mean by cleaning is things like outlier detection, missing data filling, fixing the timestamps. I mentioned that the timestamps are recorded, so everyone wants to re-window their data in a variety of different ways. And it makes very little sense usually to do that actually in the application if you could do it somewhere else, because it'll be more efficient and everybody has the same problem. So those 5 lines of MATLAB that you all wrote to put it on a common time base are sort of redundant. And the general goal here is to get the data into your application as fast as possible in a very usable form, so that from there people can build the kinds of visualizations and models that are actually really interesting. And doing this, we want to provide a uniform interface for all these multiple uses, whether it's analysis, which generally means loading your data into MATLAB or NumPy, or whatever it is. Visualization, which is different. Often today that's delivered through a web portal or a web page, and so providing a REST API for that. Or even actuation, where we're looking at a filtered stream of time series data, making a control decision, and then feeding that back into sMAP. And so I'm just going to talk about this a bit briefly, but generally the interface applications use in order to talk to their data is a sort of declarative query interface that lets them make SQL-like queries on tags. And if you remember, the tags were things like the source name. And here we're pulling out all the distinct source names which the dents are attached to. So in query, this will pull out one for Quarry Hall, and one for Soda Hall in our current deployment. And so this is just sort of the getting started at diving into the data. On the cleaning side, we allow applications to pass along a pipeline of operators that'll get applied to the data on the way back to them. So a really common thing that people want to do is add up a bunch of data. So the data center power is the sum of these 5 racks. Add it up for me. And that actually implies that you re-window it, because in order to add up time series data, you need to make the timestamps line up. And so in this second query, what we're doing is first, now you read these sort of bottom to top, first selecting out all the data center feeds, which we've tagged with system equals data center and kilowatts, windowing them on 15-minute boundaries, and then adding them up over the last day. That's what this does. The now to now minus 1 day is adding up the data center feeds over the past day. And the output is just more virtual time series sMAP feeds that you can feed back into the repository, or you can consume immediately, or you can throw away. And the operators are, again, the point of them is to get them into your application in a filtered, processed form as quickly as possible. And they're basically just like Unix pipes, where each operator runs on the data and then sends the data along to the next operator. Except for one really key point, which is that the time series data is processed alongside the metadata. And what this means is that the operators have a chance to inspect the metadata that's coming in, change it, and then pass it on to the next operator. And one example of this is each operator sort of includes in the metadata what it did to the data as a form of provenance tracking. So by the time you get to the end of the pipeline, you get back not just your data, but the exact sequence of operators that was applied to it to do the cleaning. And this is really important, so that if you have something in your database that was generated from other data, then you can figure out what exactly was done, when was that processed, what was the state of the database when this happened. Right, and so the operators, a really simple operator is units. This is a popular one. The data comes out with all sorts of weird units, and you generally want to convert it into Celsius or something. And so this is an example of a sort of unitary operator, which just operates on each element of the input separately. But you can get much more complicated operators once you get into the streaming cases where they have a history. And so part of what we've been doing is specifying exactly how much buffer, how much lag is each operator going to have. If I'm looking at a window, when am I going to get an output from it? And this becomes really important for control applications. Now, another element of scalability is being able to scale up to large numbers of points and large volumes of data. And the write workload for this is pretty much all of these sMAP sources, which are sending us physical information that's trickling in as it's generated. So the actual write workload consists of a very, very slow append to a relatively large number of streams. Most of these sensors simply either can't or won't sample that fast, or it doesn't make sense to. So for instance, with temperature, sub-hertz temperature readings, I haven't found anyone who really finds them that useful for building control. Maybe there's some other applications, I'm sure, where they are. But essentially what you have is a giant number of streams where you're very slowly appending data to them. But occasionally you have a migration or an existing database that you import. And in that you need the ability to import large blocks of data at the same time. And so what we've done in order to help this scale, especially compared to relational databases, is to build a special backend that's optimized just for this type of workload, where we store each reading in a bucket with other readings of similar timestamps indexed by B trees. And then compress those buckets using some time series compression algorithms in order to reduce the size on disk. And then those eventually get written out to a page. And this really helps your performance and your scalability, because not only you have to do much less disk I/O in order to read back your data, and once you get it in, more of it fits in memory because it's compressed. Another kind of interesting aspect of the write workload is that it's essentially forever. This is sort of a trace from a random day in May when we were just looking at the write workload coming in. And what you see is, generally there's sort of 300 to 500 writes a second with occasional spikes up to 150,000 points when somebody's doing an import from an existing database. And so this sort of is where we got our intuition that this was the right workload to optimize from. Another thing we can look at is the compression performance on some real data compared to a few other things you might do. You might put it into MySQL and Postgres. I've had a lot of people come up to me and say, well, are you putting your data into MySQL? How did you get that to work? And I said, no, we didn't put it into MySQL. And this is why not. I know the numbers are a little small here, but essentially this goes up to about 1 gigabyte for 10 million readings, which in time series land really isn't that much data. 10 million readings is like 1 a second for a year for like three sensors. So you're going to have way more than that data. And in Postgres or MySQL, using the green and black lines, you easily get up to 800 megabytes because their compression just isn't that effective, and the per row overhead is really high. But if you do the right sorts of strategies for mitigating the tree overhead and the compression, you end up with sort of an order of magnitude better. And this essentially means that you can store at least 10 times as much data for a given disk as Postgres or MySQL. And you can also kind of see here in the same kind of figure where ReadingDB, which is the backend we're using in blue, the queries are also much faster. Here, smaller is better. It's the time to extract a fixed set of data from the database as a function of database size. And the real other scaling issue that these other relational databases have is that this is a fixed size chunk of data that we're pulling out. The database is getting bigger. The queries are getting slower. This is bad because you would think that at least if I'm not moving any more data, it should cost me about the same every time. And so this is sort of a key reason why some of those other solutions end up not being scalable. Finally, now I'm going to get into a bit of the fun part and just talk about sort of some of the cool applications we've built using this data, the kinds of things you could use if you imported your data into sMAP, and a little bit about where we're going with this. So like I sort of indicated at the beginning, the basic thing you generally want with time series data that you have to have is a plotting interface or a trending interface where you can look at your time series. And so this is ours. It's plotting DOP HVAC feeds, which is the 5th floor of Quarry for some day last year, I think. And you can see the chillers cycling. There are a bunch of chillers, and then there's some supply fans which shut off at night and turn back on in the morning. But a really key question that we tried to ask in order to make this something that would be general and usable for other people and not just sort of a one-off plotter where you have to know what the feeds are is this challenge of multiple views of the relationships between all of your data. So for instance, in this example, one key view is the electrical view because we're measuring electricity data here. So what's the flow of power through the building? It comes in through a 12.5 kilovolt transformer in the basement, gets distributed into 480 volt panels throughout the building where it gets stepped down to the outlets. What's the relationship between all the meters in the building? How do you figure out where you are in that tree? But these are also mapped into an almost orthogonal view, which is the systems view. Here's the DOP HVAC loop, which has a number of fans and pumps attached to it. They're electric, so of course they're powered by the same electricity distribution tree I just mentioned, but they're not really organized that way. It's not like there's a node in the electric tree where you say, oh, that's the DOP section. No, they sort of get wired into whatever panels are convenient when the installer was there. That's not entirely true, but it is true that it's certainly not a nice mapping. And then finally, there's just the, where is all this stuff view. Where did I put that fan? And so what we've tried to do in the plotter is give people a language in order to create these different views on top of the same underlying time series data. And so here are 3 views of different things that are completely different ways of slicing the data. On the left, we have the CEC testbed where we have a very functional view. We have it grouped by data center, elevator, HVAC, lighting, micro lab, things like that. And then you can dive in and see under each of those, well, there are 3 elevators, and then we could actually dive in some more. A different view of electric loads, though, might be an appliance view, which is much more functional. And here the taxonomy is taken from some work at LBNL where they categorize all miscellaneous electrical loads into 3 categories and 2,000 subcategories. And so you might want to view your data organized by category, so I can plot all of the electric tea kettles that I'm measuring, see when they're on for a usage model. And then finally, sorry, it's a little hidden, but on the right, there's sort of the campus view, which is the spatial view. What are the buildings? What are the feeds in the buildings? And so how do we build these all up in a way that's where it's easy to make new ones? And the way is by combining that tag query language with sort of a domain-specific language for specifying what you're going to show in each level of these trees. And I sort of put in bold the important things here. The other is a little bit of boilerplate, but this is the actual code that's generating the taxonomy tree that you see here, based on the tags that you've added. And so at the top level, you're saying, show me all the source names where it has an end-use tag. And that's where we get the Rad Lab deployment, the David Culler residence, a few other ones. Then what are all the end uses? And then for that end use, what are all the categories? For all those categories, what are all the product types? And what you need there is some extra organization about, if I click on that one, do I plot all the streams under it? Do I plot one of the stream under it? How do I label the stream? And so there's some extra sort of GUI setup. But basically, this takes you from a world where instead of needing to do a separate tree custom for each new view of the data, you can just sort of define the tags that you want for a particular view and then define it, and it'll get auto-generated. You can also do a lot more sort of sophisticated data-intensive applications. This is one that one of our partners at the Center for the Built Environment has done, this performance management protocol that's looking at a lot of different data that's coming out of some buildings that they're in, trying to develop a protocol for measuring how comfortable occupants are going to be in the building. And so this has a large number of views of the data that are generated using data that's been pulled and cleaned out of our archiver interface, but then has a significant amount of sort of application and domain knowledge baked into how it's displayed. And I think the real win there was that instead of needing to bake their own database and rewrite all these common operations, they're able to just sort of have it hosted against our database and really focus in on what's important. And then finally, we have the campus portal, and this is sort of the yes, it's easy to version. I had one of my undergrads work on this for about a week or two, and he got this really nice looking jQuery UI thing going where you can click on all the buildings on campus, see their power feeds, and it's even got some interesting analysis features. If I hop over to a browser, you can see sort of the obvious things, like we can click on Sutar Jadai and get out the data. But it also compares our energy consumption today to a baseline that's generated using ridge regression models. And you can also dive in across campus and start looking at all buildings across campus by a bunch of different metrics. So whether it's peak to average, or baseline deviation. Some of the baselines are broken, so we don't necessarily do that well on all of them. But already starting to get at something that's a lot different from your usual energy portal, where it just kind of tells you, what's the current kilowatts. And because of the real-time feeds, a lot of this is sort of live updating. So while you're sitting there, the data will stream in. It's not very interesting, but it certainly comes in. Another cool one we've built is it's using a ton of data from this is this room comfort control application that's live in Sutar-Jadai right now. And so basically what this lets you do is go to a web page, look at, for your room, the room you're in right now, this is the room we're in right now, and ask the system to make a change to the building management system for you right now. So I'm not totally sure if this will work, but I just told it to cool us down in here because maybe it's getting a little stuffy. I can hear it already. And what that's actually doing is closing the loop, to a large extent using sMAP to grab the data, figure out where the actuation points are, send them commands, and initiate a command sequence that's going to open the air damper in here and stream us in cool air. And so switching maybe over to the final little demo with this plotter, this is sort of the default view that I was describing a few minutes ago. And this is, again, for this room. We're in Sutar-Jadai zone 3-07. And if we do an auto update, we can probably see that the airflow went up a bunch. This is about when I started the talk. So if that blast works, it'll go up even more. But it's in response to the temperature that's happening. And so all these types of real-time views of the data are really enabled by this underlying stream of data coming out of sMAP. And you're welcome to visit this web page and poke around and see what data is there. We have lots of weather data and a bunch of buildings. And so just to close with a note on where we're going with this, I talked a lot about time series data. This is a much too dense slide from a recent paper we did where we're trying to take this and really finish the step of closing the loop and not just get that time series data and put it in a database for applications and give you the ability to clean it, but also make that reverse path that I just showed you with the control really robust and really reliable so that all of these great model predictive control algorithms and planning algorithms and all the other ones can actually be implemented on top of all these heterogeneous separate vertical stacks. And I guess I'm a little short, but that's about it. I just wanted to sort of finish off with a plug for the project. We've got releases up on Launchpad and PyPy and Google Code. You can download it, try it out, commit it. We've got a pretty good base of users that are sort of feeding back, mostly just through emailing me at the moment. But 5 or 6 really pretty substantial uses of it. And you can use it either in the sense of downloading and trying it, or just pulling the data down from campus, or the temperature data, or the BMS data, some of which is better organized than others. And finally, last year we got the Chancellor's Energy Innovation Grant or something. So we actually have some resources now to hire a full-time staff member to work on this. So if you know anybody, it's a pretty cool project, and I hope that you can point them towards this talk. And it's not just what it is now. We're going forward with it. So there's some pretty cool opportunity to really get this going. So with that, I'm happy to take any questions people may have.
Okay, great. Thank you, Steve. Any questions?
Hi, Steve. Nice presentation. I'm a researcher at Lawrence Berkeley Lab, actually, and I've looked at using sMAP or sMAP for some of our applications. And I'm not a programmer per se, but I wanted to see if I could use that to pull data from a vendor side, a third-party vendor who's making the data available to us using REST API. And I've seen in one of your slides that one of the data sources can be REST APIs. but I just wanted to talk to you, or maybe you could shed some light on what are the requirements for me to enable this this facilitation. I have installed an sMAP instance on my home computer.
Cool.
But I just don't know where to take it from there. I have the API, I have the sMAP, but I need the missing piece.
Cool. Yeah. Well, generally the way we do the integration is the library that handles all the data publishing is all in Python. So you generally write a little driver file which speaks whatever native protocol you're sucking data out of, whether it's Modbus or in your case some REST APIs. Interprets the response and then passes the data off into the sMAP library to get published. And there's some examples of consuming REST APIs. For example, a lot of the weather data, we have a Weather Underground driver where you put in the station ID and it starts pulling real-time data from Weather Underground. So that might be a good example starting point. But feel free to shoot me an email.
Where do those examples live?
They're all in the Google Code site. Yeah.
So in terms of your back end, like your whole database reading DB, is that all? Is that you were saying an instance? Do you have like a virtual machine kind of version, or is it an install on Linux, or?
Yeah, it's a GitHub project. It's uses Automake. You can just build it.
You can just build it on
Linux. Yeah.
on Linux. Does
Yeah.
Does
It works on OS X and Linux.
OS X. Okay. Thanks.
And it's never lost data yet.
Hi, I love the presentation. Fantastic. I had a question specifically about the sources of data and thinking about having sources that may be present sometimes versus other times, right? The example would be, you know, if you're collecting data off like a person and you have people moving in and out of the building and stuff. And I was wondering if sMAP was built with that kind of thing in mind, and maybe how it might be scaled towards something like that, where, you know, not just like these set of sources that have entries in the database, but maybe sources dynamically moving in and out.
Yeah, we have some people who have done it on phones. The real challenge for who have like implemented data sources, publishing data from phones, the real challenge there then is sort of figuring out, you know, either where to publish it to or how to locate the data that's located in an area that you're interested in. The metadata store is sort of scalable, but much less scalable than the data store. And so generally the way I recommend people to do that is to sort of add new data streams that have location data, so either lat-lon or, you know, coded data, and then pull that out and generate tables of where the actual data is. It's sort of a halfway answer, though.
So are you using local time, UTC time? What kind of time are you using?
So all the timestamps are transmitted in UTC milliseconds to give the, we're Unix time milliseconds, which is unambiguous except for 9 leap seconds. We mainly did that for efficiency, just because the only really unambiguous time format I could find was ISO 8601, which is very verbose. But yeah, it's UTC milliseconds. And then some of the mandatory metadata is local time zone. And so all the display tools do the time zone conversion when you do the display.
Hi. Just a further question on sources. Have you looked into accessing data from building information models or from whole building energy simulation models?
Yeah, so we have some other collaborators in our group who are looking at extracting sort of higher level metadata that can't be expressed as just key value pairs from BIM, from Vim, like IFC models. Trying to get some Revit models that we can poke around with to try to get really these functional relationships. Because I sort of agree, there's a higher level of knowledge that you would want even above this. And so generally they've been building on top of this. So they'll take a sMAP feed, which is a time series, and then attach it to a point in a richer model for the system. The focus of this is really on the time series, whereas the focus on those needs to be also on the entities that you're modeling relationships. Like like I sometimes say, there are no chillers in sMAP. There can be things, data feeds that are tagged saying they're coming from a chiller, but it's not really the same thing. So that's sort of ongoing work. And that's sort of in the spirit of this BOSS work for the building operating system, where the other component is this. So sMAP is this bottom box at the bottom, which is a hardware abstraction layer that's providing uniform access to all of the sensing control points. The abstraction layer is responsible for mapping all of those into higher level abstractions. So there's a split.
Okay, so that answered the question on building information models. What about whole building energy simulation models and output from them? Because there's very little metadata available in the output.
Yeah, I'm not as familiar with those. We did have some engineering master's students who trained Energy Plus models against real data from SDH. I'm not sure what the state of that is.
Sure. I mean, it's a problem I'm facing at the moment, and the context can be quite difficult to extract.
Yeah.
Okay. We should talk afterwards. I've written 2 papers using RDF for similar type applications, not as technically deep as your own, but more broader perspective, especially at the organizational level. So
that'd be great. I'd love to get the references too.
I think in that particular one, they more or less hardwired the set of outputs from SPAT into the Energy Plus, and then the set of outputs from Energy Plus. So they really didn't have epistemology or anything that would capture the relationship.
Right, yeah, and that's sort of similar to what we did in this building for the blast kind of thing. And the real goal of this is to really enable portable applications so that your MPC controller or your blast could run, in many buildings that look superficially similar. VAV buildings, stuff like that.
Any other questions?
I must have missed it. What are you using for a time series database?
It's called ReadingDB. It's built in-house. We built it. It's on GitHub.
Thank you very much, Steve.
Thanks.